Hello and welcome to today's episode of the Virtual Speaker Series. I see the Zoom room is filling up. While you are waiting for the program to start, which will get started around 12:02, go ahead and let us know who you are and where you're Zooming in from. Drop that information into the chat so we can formally welcome you into today's virtual speaker session with Dr. Erica Smithwick. She is Distinguished Professor of Geography in the Department of Geography. She's the Director for the Center of Landscape Dynamics in Earth and Environmental Systems. Thank you all for tuning in. I am hearing the chimes on Old Main, which must mean we are right around the noon hour. We'll get started at about 12:02 with our presentation. Thanks for joining us. I see Ellen Gerhardt from Huntington, Pennsylvania has joined us. Welcome, Ellen. If you are just joining us, go ahead and tell us who you are and where you're zooming in from today for today's edition of the Virtual Speaker Series. We'll be getting started in just a minute or two. Thanks for joining us. Good afternoon, Penn Staters, and thanks for joining us. I'm Paul Clifford, CEO of the Penn State Alumni Association, and I'd like to welcome everybody to today's virtual speaker session, which is being recorded. Live closed captions are available for this event. You can access them by clicking the closed caption button at the bottom of your Zoom video window and then clicking Show Subtitle. You may also customize your caption view by clicking the Stream to Text link posted in the chat. Today, I'm pleased to welcome Dr. Erica Smithwick, who is the Distinguished Professor of Geography in the Department of Geography. She also serves as the Director of the Center for Landscape Dynamics in Earth and Environmental Systems Institute and an Associate Director of the Institutes of Energy and the Environment. Using case studies from the Menominee tribal nation in Wisconsin, Yellowstone National Park, and southern Kenya, Professor Smithwick will share insights into the factors shaping landscape change, as well as the factors that can support landscape resilience. She will conclude her presentation with a discussion of a new training program that is supported by transdisciplinary skills of Penn State graduate students so that they are prepared to steward these landscape futures. Professor Smithwick directed Penn State's Ecology Institute between 2017 and 2021. She's also served as a Fulbright Scholar in South Africa. Professor Smithwick has received numerous research awards focused on problems that require transdisciplinary teamwork to address complex environmental challenges. She is trained as a landscape and environmental ecologist. Her work aims to support sustainable land management decision-making under climate change, with a particular focus on forest resilience to wildfires and natural carbon sequestration strategies. Thank you for joining us, Professor Erica Smithwick. We will turn it over to you now.
Wonderful. Thanks for that introduction, and it's great to be here. I'm really pleased to have the opportunity to talk with you all about some of my research. And I have a lot to share, so I hope I can get through this. I'm going to go through it relatively quickly, but I hope we have time for discussion. All right, so I'm going to go ahead and share my screen. Hopefully you all can see that all right. So without any further ado, I'm going to jump right into it. I'm going to start off by talking about why it's important to support decision-making, particularly as we are guiding complex landscapes through periods of uncertainty. Climate change is something I'm going to be talking about today, but also the impacts of climate change on disturbances and associated threats such as land use change. How do we work with managers to promote landscape resilience moving forward? And I'm going to share 3 case studies very quickly about how this work is applied in very different settings in my research, and then hopefully have some time for questions and discussions. This is a figure from the most recent IPCC AR6 working group report on the physical basis around climate change. I'm sure you've seen pictures like this before. Happy to talk about it in more detail. But essentially what we are seeing here is that humans have warmed the climate at a rate that is unprecedented in the past 2,000 years. This is observed warming, and we can now actually take back the carbon dioxide concentrations back hundreds of thousands of years. So a lot of the carbon dioxide release is actually baked into future warming as well. And that is causing a significant amount of changes across ecosystems. So the dark blue here are where we have high confidence that these systems are being changed. So all across different biomes across the world, we're seeing changes in ecosystem structure, species shifts in their ranges, as well as the timing of their processes, which we call phenology. So just squint and see all the blues. That means we have a lot of understanding about how these processes are changing moving forward. And we also know that these changes, and this will be more of the focus of this talk, these changes are going to impact things that people depend upon. So things like water scarcity and food production, all of those negatives there with high confidence, health and well-being, impacts on cities, settlements, and infrastructure. So by this most recent report, which was released last year, we have a lot of information about how different systems are going to be affected. And it's going to get complex, right? It's going to be really hard to navigate across all of these different pressures on different systems in complex societies. And so what this really means is that as scientists now, our charge is to support decision makers, because decision makers really can't agree or don't understand some of these critical variables, how they're going to interact in the future, what their impact is, how they're going to be distributed. And this can lead to potential divergence in outcomes or a reduction in the potential for people to actually have the capacity to adapt to these changes. So the role of science these days is really towards guiding decision-making that can support more robust decisions moving forward. So how do I approach that in my own research? So I'm going to talk to you about wildfires. You obviously understand that wildfires in the Western US are changing. We're hearing almost every week about a new wildfire situation, particularly in the early fall and the summer dry periods. When I started studying fire, it was actually a couple decades ago during my postdoc, and it was focused on the subalpine regions of Yellowstone National Park. And at that time, a lot of this system had been recovering from a large fire that occurred in 1988. When I tell my students in the classroom, about this fire in 1988, they weren't even born. This is ancient history to many people. But in 1988, almost 40% of the park burned. At the time, and let me know in the chat if some of you remember the news stories around this. Yellowstone is the world's first national park, and people saw it burning, and there was obvious concern about what this was going to do to the future of the park. And it turns out that we now look back at this as being one of the first sort of mega fires that launched some of our large wildfires that we're seeing now. This image on the left is the area of the 1988 fires that burned, and then the area in the orange is the previous fires of the last 100 years. So you can see by that scale, the scale of the impact of this one event on reshaping the landscape. But what was really interesting is that the science of this actually meant that we needed to go a little deeper to understand what was really happening in that landscape. So the tree species that dominates a lot of the upper plateau of Yellowstone is called lodgepole pine. And it actually has the capacity to have cones that are called serotinous. And that means that they're actually sealed tightly shut with resin. And that resin doesn't let go of itself, doesn't release the seeds unless it burns. So in fact, those trees require fire to release their seeds. Some of the trees that are lodgepole pine don't yet have those closed cones. They actually have open cones, and a few seeds are released each year. And it turns out there's this really interesting altitudinal dynamic. So if you're actually in the lower elevation, which is drier, you're more likely to have serotinous cones. So it seems like there's some adaptation to fire in some of these regions. And then at higher elevations, you might be more likely to have open cones. So depending on what part of the landscape you were in when these fires occurred, you had different kinds of resiliency in the landscape. But by and large, most of these areas actually, following the 1988 fires, had trees come back into the system. And this is a sign that if you've visited Yellowstone in the last 20 years, you might have seen signs like this, where it was really important for managers to communicate to the public that actually these systems were naturally reseeded. Like, people didn't go out and plant these trees. There was capacity in the system to regenerate, even following one of these super large fires. And so that's kind of interesting, right? Well, we've come to understand that these systems are actually used to fires every 150 to 300 years over the past 10,000 years. So through the Quaternary, these systems have burned on a regular basis, but it's a long window of burning. So talking about fires as resilient to systems is kind of a new thing to be thinking about. But again, as of 20 years ago, that was what we were trying to understand in this landscape. So here's an image of a burn that occurred in, well, we started studying it in year 2000. So here's just about 10 years following that burn. And you can start to see some trees coming back in the landscape here. You can see some seedlings. And if you come back to that landscape like 17 years later, this is kind of what it looks like. So again, we're seeing recovery of these systems 17 years following the fire. So things seem hunky-dory in this particular landscape. But what was interesting when we started to then think about, well, I wonder if things are changing due to climate change, we did some modeling work, and we published a paper in the Proceedings of the National Academy of Sciences that actually showed that if we carry forward the kinds of climate conditions that were present in 1988 that preceded and caused the high winds and very high drought conditions of 1988, and we look forward into the future, we can predict when those climate conditions are likely to occur, and thus when fires are likely to occur. And here what we're seeing, this is the total greater Yellowstone ecosystem burned area in 1988, moving up through our observations. And then moving forward through time, we're starting to see burned area exceed what was burned in 1988. And if you do the math on this, which we did, and we did in this paper, the area burned, the frequency of burning will increase by an order of magnitude. So where we used to have fires every 150 to 300 years, we might have them now every 15 to 30 years. What will that do to the system? So we've, again, documented that these fires are associated with changes in climate, particularly the spring and summer temperatures, and could cause very different kinds of fires moving forward into the future. And in my own professional career, this has been borne out. So those same stands that I studied for almost 20 years burned again. So across the road from that 17-year-old forest is this. This is a fire that came through that Yellowstone landscape after 17 years. And what did we say? It was supposed to not burn for another 150 to 300 years, and it's burned after 17 years, exactly what our models were actually predicting. So, and you can also see from this image how severe this fire was in terms of the charred material. Now, good news is that we've gone back since, and there is some recovery even in this system. But the question is, how much can this system get repounded again and again until they don't recover? So a lot of my research is now thinking about the resiliency of these systems and the capacity for them to recover, but it's also in the face of other threats. Like, this is cheatgrass. Cheatgrass is really good at carrying fires, and the mountains in the background are the Tetons there, just south of Yellowstone. We have found cheatgrass up in high elevation systems just south in the greater Yellowstone ecosystem. So we have these other compounding threats also affecting the system. And all of this is playing out on landscapes that are really complex. This is, again, an area in southern Greater Yellowstone ecosystem, just south of the Tetons. And you can see that there's heterogeneity in what different portions of the landscapes have experienced. So over here on the left, we have some really recent fires. Here we have some areas that haven't burned in a while. But it's, in terrain that's really hard to manage. So if we were to support managers to say, well, actually, in some areas, you're likely to be fine because there are serotinous cones, but in other areas, maybe not so much, and you might need to do some more proactive management. How do we advise managers where to go and what to do? And so we're starting to work on that. We're starting to think about seedling resilience, where seeds are likely to propagate, and what traits those trees have that will allow them to be successful in certain environments. My graduate student just did a geospatial analysis on this, and we're looking at things like the seed sources that are available for a given landscape context, the kind of terrain it's in, as well as the kinds of resources it might need at a local level, like how much water is there, soil nutrients, and so on, that might support resilience. And we can now, the darker areas here are higher proportion of presence of a given tree species. So in this case, it's subalpine fir, and we can identify the kinds of conditions, like the amount of seed source area and the kinds of aspects that would be most likely to support resilience for that tree species. And so this, then we can tell to managers, well, hey, if you want to plant subalpine fir, you should do it in these kinds of areas. Okay, so swiftly, given the interest of time, I'm going to move on to another project. This is called Visualizing Forest Futures. It's working in northern Wisconsin and in collaboration with the Menominee tribal nation. Our partner is the College of the Menominee Nation and their Sustainability Development Institute. The Menominee Reservation can be outlined here from this Google Earth image. This sort of rectangle that's missing a section here is the reservation. You can see it clearly because it's dark green, and that's because the Menominee manage their forests very sustainably, and forests are their livelihood. You can see, and this is a very small portion of their original homelands. Right now, north of the reservation are the Chequamegon-Nicolet National Forests. So our study area is kind of this entire blob that includes these national forests, the reservation, and other private lands. And within this area, you can see that there's variability in the kinds of vegetation that actually exists. And so it's a good landscape for us to understand in climate change how these forested systems might be changing. Now, in this area, wildfire is not the issue, but they are very interested in, well, I shouldn't say climate change is not the issue. It is the issue, and I'll talk about that in a second. But there are other factors that are also at play. So again, unlike a national forest, this system is very heavily managed. And the image on the top left is the Menominee Tribal Enterprise Sawmill, which is very productive. And again, given its forest certification for sustainability, it actually markets for that. So it wants to manage its forest sustainably. And then the Chequamegon-Nicolet is also managed pretty heavily by the Forest Service for timber as well as other ecosystem services. And in their management approach, the Menominee have identified a sustainability model that goes beyond people, planet, and profit to identify the role of technology, land and sovereignty, institutions, human perception, activity, and behavior as all being critical for that management. I'm not going to read this to you, but you can sort of see here, Chief Oshkosh, who actually was sort of given the false choice of where do you want to put your reservation, chose the area that was within his original homelands rather than moving out to Minnesota so that he could manage this landscape with forestry in mind and given that vision of sustainability. But as I mentioned, there are threats to this forest. And one of them is that given warming temperatures and more extreme temperatures, previous work has shown us that some species are likely to move north, some species in the south are likely to move in over long periods of time. How will this change their approach to forest stewardship and forest management? That is the question. And what kinds of new threats might emerge, like pests and diseases? And one of those threats is the emerald ash borer. We have emerald ash borer here in Pennsylvania, and you can see this map in the middle is the potential threat of emerald ash borer across the Midwest region. It's not yet in the reservation, but it's nearby, and so the Menominee are very concerned about what this will mean for their ability to harvest ash. Now, it turns out ash is actually not just important for timber purposes, but also has a cultural meaning in the system and is useful for other kinds of livelihood processes. And so this one species, even if it is lost from the system, has meaning for the Menominee beyond just the timber meaning. So we used a forest landscape simulation model that can model tree growth, tree death, as well as some of these threats. We can spatially propagate disturbances like windthrow or fire. We can also spatially propagate impacts on pests and pathogens like emerald ash borer. And I'm not going to go into a lot of detail about this, but just I'm happy to if there's questions. We drive those models with geospatial maps. The two on the left are of soils. So we need to know what kind of soil texture that is so that we understand how much soil water that is, so we understand how trees are able to grow. And we also need to know what kinds of initial vegetation is there. This rainbow map on the right is the forest inventory and analysis map of what trees are there. And you can see how diverse the system is. And then we run the model under different climate scenarios that are taken from large global scale estimations of how the future might change under different scenarios. And we actually can then collapse some of that information to understand that in the bottom right, I guess you see the different kinds of climate zones that we predict are in the region. And we use that to simplify the climate information and to drive forward some of these landscape scale models. And to make a long story short, what we've found is that the spatial resilience of this landscape is variable across the landscape. So we've been able to simulate both emerald ash borer and windthrow. And here in this map, you'll see that the red areas are actually showing lower resilience, which means that the same species that were disturbed don't come back. We have a different kind of forest at the end of the simulation period than we did at the beginning. And there's patterns to that resilience across the landscape. So again, like in Yellowstone, we can spatially target which areas might need more support if they're going to be managed for those initial conditions. We also can simulate, the kinds of species that are likely to move into the area and ones that are likely to move away. This sort of beautiful rainbow ribbon map shows us that northern hardwoods are likely to increase, but then stabilize. But southern hardwoods, which again, like those drier conditions, are likely to come in to the region. So again, we've only lost one species like ash in the system, for example, but we've been able to show that there are still changes happening in the system due to succession that was in the system, due to climate-driven changes. All of these things are happening at once. And overall, if we actually look at changes in biodiversity in this landscape, this is the mean species richness of biodiversity through time. The top line is sort of how we might expect biodiversity to change. And what's interesting here is that under regular climate conditions, we're seeing an increase in biodiversity, and that's because of that initial successional changes that are going to emerge, but the kinds of species might shift. And then what we're seeing, however, under climate scenarios is that all the climate scenarios, even though there's that increase because of successional inertia, we're also seeing declines overall in biodiversity, and we can attribute that to changes in climate dominantly. Okay, so again, lots of stuff going on in this slide, but basically we run all sorts of scenarios with this model. We can look at different kinds of management options with harvesting, different wind, different climate, and we can look at how the model uncertainty might propagate. And then we can look at different metrics of how to evaluate the model outcomes. And what I want to show here is that there are going to be trade-offs or co-benefits across different objectives that people want to manage for. So what I've plotted here is total carbon, so how much carbon that forest might hold, plotted against how many, the relative importance of culturally important species. So you can think about that ash species, for example. And the the colors represent different scenarios of warming. So the closer you are to the one-to-one line as you move up to the upper right, the more both objectives are maximized. So under the less warming scenario, we are in general maximizing both of our objectives. But if we go to the red area in the lower bottom, we're heading towards the origin, right? Both benefits are minimized. And so what this says is if we lessen the amount of climate warming, we actually have more opportunity to maximize across multiple benefits. Whereas if we have more warming, we're constraining our opportunity to balance different objectives. And then within each of those climate areas, we have management strategies that are both more winners than losers. So for example, we can do uneven age management where we select different ages for extraction of timber versus clear cutting. Those seem to provide more benefit across these particular objectives compared to others. If I had put economics in here, we might see different kinds of scenarios be winners. So there's a lot going on in that graph, but the point is that there are strategies that are going to meet multiple objectives that we can clarify and give that information back to managers. So, okay, we can do all this stuff. We can learn about all of these trajectories. We can learn about how it compares to initial conditions and patterns. But how do we actually make these results meaningful? So that graph I just showed you is pretty complex, and I can talk you through it, but there must be other ways that we can communicate some of this. So in this project, we're using virtual reality to actually translate those model results into a way to tell stories about forest futures. And we think that this is important because people can be actively immersed in decision-making. And by talking to people about what they see or don't see in those stories, we can access their values about different strategies, about different forest outcomes, and thus the values that might lead to those outcomes. In other words, you can't be in forests of the futures today. So how do you know how it's going to feel? Like, what kinds of decisions might you make today if you knew that this was the outcome? But being more immersed in that outcome makes those decisions more palpable, more realistic. So I do have this little video. I don't know if I have time to watch it. I'll just do a couple seconds of it. Where we have actually tried to simulate different kinds of forest conditions in the future. What you're seeing here is trees, obviously, that are artificially designed to represent some of these forests of the future. These are all data-driven, which is to say the model tells us how many kinds of tree species, what different ages they might be, and then we translate that information into a simulation that people can experience for themselves. If I were to show you more of this video, hopefully you can see me. Yeah, so over here you can see there's someone actually interacting with the VR, and that person can actually toggle different information about the scene. So if they want to look at a particular species or a particular climate outcome, more information is included in that image. So that you don't get dizzy, I'm gonna carry on here. Okay, so that's one fun thing that we're doing in that project. So now I'm going to a little bit of whiplash, take you all the way to Kenya. What are we doing there? Well, we're trying to take some of these ideas and say, okay, we know these systems are changing. We're thinking about new ways of interacting with managers. What about ways to design new management strategies that we can actually create landscapes that are thriving? So when we think about regenerative, we're thinking about systems that aren't degrading in the face of these threats. They may be resilient, but sometimes you want to go beyond resilience. You want to actually create systems that are better than what you had before. How can we create those? This is particularly important in agropastoral landscapes in this region that are under multiple threats. So a lot of what we're working on is these arid and semi-arid landscapes, ASALs, which have millions of agropastoral people and communities that are highly vulnerable to climate change, really already living on the edge, and then you introduce climate change. Only 20% of the area in Kenya is arable, and there's significant land use changes in addition to climate changes. But climate changes themselves are causing already observable declines in yield, as well as increased pests and pathogens and diseases, even locust threats you might have heard about a few years ago. All of that is happening on land policies that are not necessarily allowing people to adapt to these changes in the way that they historically were able to. So we have a whole project that I'm not going to go into detail with, but we're looking at water availability, we're looking at those policies, we're looking at how that affects people's livelihoods to try to model regenerative landscape futures. And I'll just share a few things. And this area is part of the Masai Mara landscape. So the agropastoral herders would traditionally migrate to new lands if there was drought, right? They'd go to an area that was more productive. What we are doing is actually thinking about how, here you can see the Masai Mara game reserves, and then we have identified some study areas that actually used to have a traditional land policy called group ranches that constrained people to live in a certain areas, and it constrained some of that migration in times of need. Some of that landscape transition was unsustainable because it forced people to for lots of reasons, for social reasons, but also for biophysical reasons that they couldn't move. So some of that has since privatized. So we have this interesting area landscape pattern where you have some areas in group ranches, some areas that are privatized, some areas that have transitioned out of group ranches into conservation areas. So as a result of that, there have been significant land use changes that are observable with aerial imagery. So here you see the same landscape between 2004 and 2018. And then you also see significant deforestation occurring. Here's in the Mau Forest between 1985 and 2020. And then, as I mentioned, the locusts, again, just a couple years ago, although locusts are endemic in this part of the world, there are increasing swarms of locusts that can devastate local farmers' livelihoods and crops. So we are doing a few different things in our project. We're able to use imagery to actually track water pans. So water pans are really important for getting water to livestock, and they are drying out in many areas. And also in many areas, the water quality is declining. And so we're using satellite imagery to actually, here's our collaborators on the ground from Masai Mara University, to take field measurements and then relate them to what we can observe from the satellites. And we can develop relationships like this from the, and basically create models where we can track the remote sensing spectral signature to the water quality on the ground. And we think we can use that to help track the changes in these water pans across the landscape. We also can look at anomalies in precipitation in the past, what's happening in the landscape. And the upper right dark blue area is showing that 25% of the time the landscape is getting wetter. The orangey reds in the bottom left shows that 42% of the time the landscape is getting drier. And so these are extremes, right? And this basically shows us that it's both getting wetter and it's getting drier. And this is causing variability that farmers are having to react to. And indeed, we've also done household surveys where we've asked farmers and pastoralists, well, what's happening in your landscape? What do you think are the threats in this area? And you can see pests and diseases are 80% see that as a threat. But a lot of these are also rainfall variability, too little rainfall, too much rainfall, frost. Lots of different climate factors are also influencing what people are feeling on the ground. So in the future, again, I don't have time to go through all of this, but we're going to use a modeling approach again to try to understand in Narok, Kenya, which is one of the landscapes I just showed you, but also in Ethiopia and Zimbabwe, some case studies. Can we understand how all of these factors are likely to play out? What kinds of spatial patterns are likely to emerge if land use continues to change? And then what are the ecosystem service outcomes of this region? So this project is just beginning, and maybe you can invite me back when we finish that work and I can share more about it. But I am going to conclude. I'm wrapping up. I know I'm over time. But basically, landscapes are changing in all of these areas. I've showed you 3 different kinds of systems. They're all changing in very different ways. The climate and associated threats are shifting disturbance regimes and threatening forest or landscape resilience. And we need to identify and give people tools to proactively design landscapes that can thrive under all of these changes. I think we need new approaches. This includes things like the cool visualizations, but also really drive research that is transdisciplinary, where we're talking with communities and like doing those surveys first so we can understand what people are feeling on the ground and how research can support that. Lots of research supported this project. And because I covered so much territory, really want to acknowledge that this was not just me, this is teams of people, increasingly at Penn State. And one of the reasons I love working at Penn State is how interdisciplinary our research is. So it's very easy for me to cultivate teams across colleges to do this kind of research. I can think of no other institution that does it as well as we do. With that, I will stop sharing, and I'm more than happy to answer any questions. I know I covered a lot of ground, so please let me know what questions you have.
Thanks, Erica. We have a couple questions coming in from the audience. First question is, how does architecture tie into your topic? And what do you believe architects should focus on to usher in a more sustainable future?
Yeah, thanks for that question. So one thing I didn't have time to talk about today is a new graduate training program called Landscape U that we're in year 5 now of a NSF funded program. And in that program, we intentionally are bringing in the built environment into our understanding of sustainable systems. So I've mentioned the impacts on natural systems. I've also mentioned the impact on social systems. We often connect those when we think about resilience, but the engineering, the arts, the architecture, we haven't yet brought that into our vision of how we actually build these new landscapes. So I actually really appreciate this question because I think we need more engagement across the architectural sciences, the arts and engineering fields more broadly into these questions of how are we adapting to climate change, right? So specifically, we are working with architects on regenerative building design. Lisa Ayulo in the Hamer Center in the College of Arts and Architecture has been a partner in this, where we're thinking about what does a regenerative building mean? And really that means you're not taking from resources from the environment. In many ways, you hope that you're adding and providing more resources to people and to ecosystems. And so how do you build environments that are going to be like that? So take the building scale and then expand it all the way to the landscape. How do you design landscapes? And what's the role of the built environment in that? So lots of questions, lots of research opportunities, but I think it's a really good area of inquiry.
So as wildfires seem to be becoming more and more prevalent out west, especially, there's this debate about do you let the fires burn or do you put the fires out? We know you touched on that it's all part of the life cycle of a forest, and fires are an important part of that. Where do you fall on that? Like how should we be looking at that topic?
Yeah, good question. And I didn't have a lot of time to talk through that. So I mentioned the Yellowstone landscape, which has this capacity to recover from fire, and it has experienced large wildfires, replacing wildfires in the past. But there are other regions in the Western United States that have not adapted to those same kinds of fire regimes. They're actually used to getting fires much more frequently at a lower intensity. So these would be places in the Southwest, for example, in parts of California, where you would expect a lower fire severity or a mixed fire severity regime. And so in those areas, what has happened because of fire suppression is we have missed some of those fires. And so fuels have been built up. And so not only do you have drier conditions because of climate, you also have more fuels. And so that's really the challenge for us. And then the third sort of spoke on this is that we have more people in these landscapes. And so more human and risk of human ignitions. So you put all of these three things together, you are seeing a very different kind of fire regime than we used to see. So we yes, need to recognize that this is a different kind of fire system than we are used to. How do we manage for that, which is really your question? The truth is we do not now, because of what we've baked in, have enough resources to fight every fire. We just really don't, unless there's the federal government decides that this is going to be our priority. And so what we really are doing is trying to minimize risk to human communities and to actually fight fire where we need to protect human lives, of course, and infrastructure. That's going to be the first priority. More proactively, what we'd like to do is have more managed fire go safely into these landscapes so that you are actually removing some of that fuel risk. And in many cases, you're doing the job of also restoring some of those historical fire regimes. So a lot of my community is thinking about where do those managed fires, where are they appropriate, and how can we safely deploy them into landscapes. Hope that helps.
So you touched on climate change, and some of the work that you've done over time to see how climate change has had an impact. If you had kind of a crystal ball to look into the future, if we don't change the way that we do things and how we preserve the planet, what does that mean for the work that you're doing?
Well, I guess I have a job, yeah, but that's not the way I do it. Yeah, it doesn't look great in terms of where ecosystems are heading, nor how societies are going to cope with these extremes. And so we are, very attentive to the fact that we are going to have to do more and more work, as I've described here today, in supporting communities moving through those spaces. Again, my first class on climate change was in 1993, right? So this is something that we've known about for a while, but the real challenge is a people challenge of how we can identify the right kinds of policies and practices to adapt to the changes that are already kind of baked in, but also identify solutions. And the reason I get up every day to do this work, and the reason I love teaching classes at Penn State, is because we're inspiring people to think about the solutions. And yes, the roses, rose-tinted glasses kind of person. And I'd like to think that people at Penn State and our partners, we can identify those solutions that are going to help us best navigate some of these uncertainties. And so that's why I work now with social scientists, and I work with the engineers, and we're trying to identify those pathways that will help us move through that in the best way possible.
So Erica, just this past year, you had the opportunity to serve as an administrative fellow here at Penn State. Can you talk a little bit about that program and what that experience was like for you?
Yeah, it was a great program. So this is a program run through the Office of Faculty Affairs, basically. And what they do is, and it's not just for faculty though, it's also for staff, you are shadowing a senior leader within the institution. So I had the pleasure of shadowing Laura Weiss, who is the Senior Vice President for Research. And so for an entire year, you are sort of excused from your normal duties in the Department of Service and Teaching to really just sit and understand how the institution makes decisions. And, you've observed even in the past 24 hours that some of these decisions are really complex. And so it was a really neat window into understanding how some of those decisions are being made at the institutional level, how they are communicated, where there are failures in the system, of course, because it's hard. So that was wonderful. We also got to tour all of the as many campuses as possible through our experience. I got to tour behind the scenes at the creamery, at the hockey rink. Got to meet with you, Paul, and learn about the Alumni Association. So do things that I wouldn't normally do in my day-to-day to really understand. It gives you the full breadth of work that happens at this institution, and frankly gives you a lot of respect for the hard work that all people in our institution are doing, not faculty, not just students, not just staff, but everybody is coming together. And so, yeah, it was a wonderful experience.
Great. Well, it was good to get to know you through that process. Yeah. We have one more question coming in from Bill. He wants to know, does the fire model take into account the much reduced fuel load in a recently burned area?
Good question. Yeah, very sharp. So we do have fire models that can do that actually have fire emerge from fuels loading. The first paper that I showed you, this the PNAS paper, Proceedings of the National Academy of Sciences, that shows the reduction in fire. We actually only projected that model, and those estimates are only to the year 2050. So the title of our paper is actually through mid-century, because we actually don't have confidence in our ability to understand the interaction between climate and fuels in that particular modeling strategy. So in essence, what I'm saying is that the model that we use for that paper does not have that interaction. What we do in other modeling approaches, we can test that. I will, however, say that what's interesting is that area that burned 17 years after the fire, you could arguably say, well, are there enough fuels left 17 years? Or is there enough fuel to carry a fire 17 years into that 100-year fire cycle? And apparently, yes, because that fire burns super, super hot. So it seems that in that particular landscape, fuels are not going to be the limiting factor, but that might change. If it gets hit again and again and again, you actually might move more from a forested system to more of a savanna-like system. The way I often think about it is like, okay, we know Yellowstone is famous for its grizzly bears and the elk that use the forest in the summertime and so on. But what if it becomes more of a savanna-like system, more of like Kruger National Park, right? Are we managing for different kinds of species in that landscape? So that's one of the things that we're really interested in exploring in the future. It's a good research question.
So that's all the time that we have for today. I'd like to thank Professor Smithwick for joining us. And I also want to thank you, all of you who have tuned in to today's virtual speaker session. As a reminder, you can view the full listing of all of our events online and in person at alumni.psu.edu/events. Thank you for tuning in and for all you do for the university, for the glory, and for the future. We are
Penn State.